Welcome eNet 130 at Bellingham Technical College. This is our semiconductors course, and this is our third lecture in the course and our second lecture concerning PN junctions and their resultant semiconductor device diodes. So in our previous lecture we went over what a PN junction was. We included concepts about charge carrier passage across the depletion zone at the interface, and more importantly the energy hill that was created by that fixed charge at the interface. We went over the difference between forward bias, in which an external voltage was helping push charge carriers up or down the hill, and reverse bias, where the charge carriers in the diode were being pulled away from the interface, and therefore the energy hill was effectively being heightened and steepened, and so no current would flow. So we concluded the diodes act like one-way valves for current. They have a fixed voltage, and that they can be used in a circuit in a very different way than a resistor. We also included an equation, the diode equation or the Shockley equation, that describes how much current can flow through a diode in either direction depending on what bias we give it, what voltage drop we impose across it at any given temperature, and taking into account some constants having to do with a specific device. So that was that exponent equation that more or less defines the current voltage behavior of a diode. Okay, so in this lecture we're going to build on that, and we're going to start with some real diode specs. So there were a lot of terms in our diode equation. We'll just skim back to that real quick and refresh ourselves. So here's our Shockley or diode equation blown up here. And this again is very important because this says how much current will flow through a diode given at a particular voltage drop that we impose over it in the circuit. So we've got I sub S, the reverse saturation current, we've got some other constants, quality factor, temperature, and we've also noted, looking at scanning back down, looking at our current voltage relationship from the last lecture, we got a few things that we don't want to have happen. We don't want to oppose more reverse bias voltage than V sub R. We might want to know how much current can flow backwards through the diode at a given temperature, and we certainly want to know more about this forward bias region and how to make use of it in a circuit. So lucky for us, a lot of the things that we want to know with respect to those points are available in our diode datasheet. So for every device that you can purchase, you'll get a datasheet that basically says what not to do and what to expect if you operate the device under appropriate conditions. And so these are the data sheets, the manufacturer's data sheets. So we're going to look at a real live diode, a real live PN junction. It's 1N4148. There are lots of different manufacturers that make it, and the data sheet is represented. It's copied right in your textbook, and you can probably look one of these up online, and there are probably going to be ones put out by several different manufacturers. Most diodes are fairly generic and standard, and so a lot of major semiconductor component manufacturers would make them. So you might find a data sheet put out by many different manufacturers. Okay, so there's a lot of information in this data sheet. Let's just look at this. This is a high-speed diode. We get a picture of the physical device with a K on one side and an A on the other. And if you look at the footnotes in your textbook, you'll find that K represents really C, meaning cathode. So this is the N-type material, and the anode is the P-type. And then they give you the symbol in case you forgot what anode and cathode are, so you know that basically current's going to flow from right to left. And so the band on your physical device that you would put in your circuit is in the direction of current flow. It's the cathode. So now you know how to use it in a circuit, in a physical circuit. You're told what the packaging is. So that little chunk of silicon is sitting in the middle of a leaded glass, a little blob of leaded glass. You're given switching speed, maximum, So here's how much time you need to basically go from a negative to a positive in a square wave. And this has to do with the capacitance of that PN junction itself. We'll revisit that later with some specialty diodes that literally behave like capacitors with their PN junction depletion zone. You're given some other real important things to do, not to do. Continuous reverse voltage max, that's 100 volts. So do not apply a reverse bias voltage back in this direction of more than 100 volts continuous. And even if you only apply that reverse bias voltage in little pulses, still don't go over 100 volts. So basically you could not plug this into something that was going to apply more than 100 volts even if it was just the peak voltage, or we would break the device down. So on our, that is this value, V sub R. So that's a reverse bias max. So don't go over 100 volts. And we're told that the repetitive peak forward current is a little under half of an amp, so 450 milliamps. So what that means is, if we go back to our diagram here, when we've applied enough forward bias voltage to get this current flowing, basically giving us as much current as we want, put something else in the circuit that makes sure that you don't go above a current equal to 450 milliamps. And in fact, that's why you have, I'm doing a lot of scrolling, that's the role of this current limiting resistor. It makes sure that the current through our diode does not exceed that forward max, or you'll get the diode too hot and it won't function right. You might destroy it or certainly alter its properties, and that way it won't work predictably in a circuit. So kind of rolling those two together, more of the forward bias, we're told that the diode won't dissipate more than 500 milliwatts. So we can look at it at a little in the future how we calculate that when we pull in some circuit models, because to calculate power we need more than current, but we certainly know that our 450 milliamps is going to be a component of this. But this is how much power that the diode can dissipate before it'll get too hot and stop working. Okay, so let's dig into the spec a little bit more and blow it up so we can see it. We're given a little description of it: high-speed switching diodes and all kinds of different packaging available. Sometimes there's variations on a given type of diode that have slightly different properties. So we're given a couple of graphs, and again, this is coming straight from the manufacturer. You could find one of these yourself online. So here is a plot of the reverse, I reverse in microamps as a function of temperature. So remember, in reverse bias, the diode will only conduct due to intrinsic semiconduction of charge carriers being produced thermally in that depletion zone, and then they can zip away under the reverse bias. So we see that in reverse bias, our diode's going to act kind of like an intrinsic semiconductor, and our reverse current is going to increase with temperature. So that's not a surprise. So this is capacitance as a function of reverse bias applied voltage. So this is where we look at the PN junction depletion zone as being a little capacitor, like the dielectric of the capacitor. So we can see as we apply more and more reverse bias, we're gonna widen that depletion zone. So that's like increasing the distance between plates of a capacitor. And if you go back to your DC definitions and you look up the definition of capacitance in terms of the area of the plates of a capacitor, dielectric strength, and the distance between them, you'll notice distance in this is in the denominator. So if you've got a bigger distance between plates, you have a lower capacitance. So that's exactly what's happening here. This is a plot showing how that PN junction interface acts like a capacitor, because it does. So as we apply more and more reverse bias voltage up to 20 volts, the capacitance created by that interface drops because we're increasing its width. And we can actually take advantage of this in particular diodes called varicaps, where we have a diode that we deliberately caused to act this way in a predicted manner, and so it acts as a variable capacitor. So that's just taking advantage of one characteristic of our p-n junction. So that's been calibrated for you. So if you want to understand what capacitance your diode is going to add to a circuit, because maybe you're looking at it as an AC component, you're calculating resonance or something, and you want to make sure you understand what capacitance has been added by adding a diode, you can pick it right off the graph in terms of your reverse bias, your DC reverse bias. Okay, limiting values. Always pay attention to these first, because these tell you how your component will fail if you mistreat it. So we have repetitive peak reverse voltage. There's 100 volts, and that was stated up front. This was repeated up front, what not to do with your component. Continuous reverse voltage. So basically, don't apply a reverse bias voltage of more than 100 volts, even for a little bit. Don't apply more than 200 milliamps continuous forward, or 450 peak on a small signal. So if you're going to use this diode in a DC circuit, 200 milliamps or 0.2 of an amp is the most you can have flowing through it. So you're going to have to limit the current with a resistor with another circuit component. Non-repetitive peak forward current. So there's some other benchmarks if you just have current flowing once. And the reason that repetitive and non-repetitive are different and are different from continuous is the ability to dissipate heat between. The reason we're limited on current is current creates heat. And we diffused things to create that p-n junction, and diffusion is a temperature limited process. So we'll basically end up homogenizing the diode if we let it get too hot for too long. So the limits on current are thermally related, and so we need to respect these when we design a circuit. Power dissipation, same thing. There's some benchmarks of how hot we can get it if we're storing it. So if you have an application that you have maybe a sensor circuit inside a furnace, or outside in the desert where it could get very hot, or in an industrial application, you need to make sure that your device and the junction itself don't get hotter than this on a continuous basis, or it will no longer work the way you expect it to work. Okay, so there's what not to do. So electrical characteristics. This is how we're going to model. This is what to do. Here's what you can do with it. So we're going to use these characteristics when we make a model for how the diode is going to behave in the circuit and design benchmarks. So the most important is our forward voltage. So this is the knee, as Mr. Fiore calls it. This is the applied forward bias voltage at which we start to get nearly unlimited current through the device. So that's a real important voltage to know, because that's the point at which the diode will start conducting. And it depends on how much current is actually flowing, so the two are interlinked. But for a middle of the road, you've got a min-max, you've got a range of somewhere between 0.6 and 0.7 of a volt. And this is characteristic of a silicon device. The 0.7 volt forward bias is pretty typical. And if you're not told otherwise, that is a good number to assume if you don't know. If you don't know what type of diode you have, you can usually assume it's silicon unless otherwise specified. And you can assume it will have a forward bias voltage of 0.7. And we'll see what that means in a circuit here in the next section after we create a model for it. Reverse current. So here's if you're flowing in reverse bias, so in the direction the diode doesn't want to conduct, here's how much current's really going to flow with allowable applied voltages. See, this is way below that 100 that we didn't want to apply. So somebody's applying 20 volts in reverse and they get 25 nanoamps. Remember, the forward direction, you're getting hundreds of milliamps. Now you're getting nanoamps. So this shows that one-way direction of the device. You've got some capacitance benchmarked to frequency. And so as you remember from AC, capacitance is depending on the rate of change of voltage. So if we've got an AC signal, the frequency is going to be related to the rate of change. So we always want to measure our capacitance at a given frequency. with no reverse bias voltage. We have 4 picofarads. And then of course if we want to see how that changes with additional reverse bias application, we would go back to this graph and call it out. So capacitance recovery time, this is for switching applications or signal processing, and that is related to the capacitance. We won't get into that in this course, but it'll be something that that's going to be related to characteristics of op amps that we'll study in another course. Thermal, this is kind of going back to what not to do. Thermal resistance of our leads in the device, basically how much heat we can dissipate. And now some more graphs about performance, mainly with temperature. So how does our forward current change with temperature? And you notice, unlike the reverse bias, now we have the current going down with temperature. And this has to do with the temperature in the coefficient of in the exponent term in our diode equation, and also allowable power dissipation. And we have a blow up of our knee of our forward current versus forward bias applied voltage, and that's just a blow up of, and a very device specific blow up of this portion of our current versus applied voltage curve. So that's the one we're usually interested in when we're looking at a circuit. So what are those curves and how they shift with temperature? And last but not least, some maximum permissible non-repetitive forward peak current. So if you're afraid your circuit's going to have some spikes and you need to account for those and have some current protection, this tells you what you have to design around. So that is pretty much everything you would need to know about how to use your device, forward voltage drop expected, reverse saturation current, and then what not to do with it, maximum applied forward current, maximum applied reverse voltage, and power dissipation. So now we understand how our diode works generally, qualitatively. We know how to go to our spec and pick off key values of what we can expect and what not to do. So now we need a model to put these in a circuit, because I don't know about you, but that exponent equation, I mean, I can plot it, it's nice mathematically, but it's hard to wrap your mind around how that's going to act in a circuit. So now we're gonna shift gears a little bit, and we're gonna look at circuit models that represent a diode and how it's going to behave in a circuit. And there's 3 simple ones that are used, of which that's the second one is going to be pretty common. You're going to see this most of the time and use it most of the time in this course. And then a really accurate one that's going to come into play when we need to represent diodes in signaling applications in AC. So we're going to start with a simple one. In its simplest behavior, a diode is a switch. So if you have a forward bias voltage applied to it, the switch closes and acts like a short. And if you try to run current backwards through it, or you apply, in other words, you apply a reverse bias, it acts like an open. So a voltage controlled switch would be the simplest way to represent a diode. A more accurate model is a voltage source plus that voltage controlled switch. And the reason we have a voltage source is we're now accounting for the fact that we dropped some voltage climbing that energy hill at the PN junction, and that's what the textbook author Mr. Fiore means with the V knee. That's that forward bias voltage necessary to start conducting that we saw in the current voltage plots. This is also known as V forward bias, or VF in some types of analysis. So we basically have this battery in kind of backwards to the direction that current would flow. And then if we want to get super accurate, we'll allow for the fact that in addition to our energy hill at the junction, which is basically like a little voltage source going the wrong way, or opposite the way we want it to go, we also have just plain old ohmic resistance. You know, the second law of thermodynamics is everywhere, and we still have some purely resistive losses getting across the diode device. It's not a perfect conductor because nothing is. So we can account for that with a series resistance that's known as R bulk. And then the most important part, each one of these models has this voltage controlled switch, which basically encompasses that one-way behavior that is so important with diodes. So if we were to plot the behavior of each of these models in a current through the diode versus voltage drop across the diode, V sub D is voltage drop across the diode. We could look at the first model, it's just a switch. So if we're applying reverse bias current, voltage. Reverse bias voltage, there's no current. Current zero. As soon as we apply forward bias, current's infinite. The switch is closed, so it's an open circuit or a closed circuit, nothing else. If we look at model number 2, we basically just offset the point at which we start getting a closed circuit behavior by the value of that forward bias voltage. So there's this offset here from V equals 0 to V equals V sub F is the V knee. So there's the action of this little voltage source that we have to oppose in order to get current to flow. So we get no current flowing, diode acts like an open, diode acts like an open. I finally applied a voltage equal to this, and now it conducts with no reservations. It gives me infinite current once I get past that. Okay, so our last model is gonna look kind of like the first one, except now once I apply the forward bias voltage, instead of giving me an infinite current, it'll give me a current that follows Ohm's law using the value of the bulk resistance. So all three of them work, but this model in the middle, this middle one is the one that we're going to use most of the time. The third one is the one that we'll use in some signaling AC applications as we start using PN junctions and transistors to build amplifier circuits. So along those lines, how do we define that R bulk? Given the fact that really that current, this straight line doesn't look like that exponent equation that we define with the diode equation. It's not a straight line anywhere. And we won't use this particular relationship right now, but we will use it when we start to define transistor models in signaling amplifiers, when we start looking at amplifier gain. So let's take a look at a plot of real diode current versus diode voltage. The red plot shows that exponent relationship that's the real behavior of the diode. So the problem with defining an R bulk is resistance is, of course, the ratio of voltage to current, right? V equals IR. Ohm's law always applies. Okay, so if we're looking at something that has a different slope with every point, which is a curve, this red line is a curve basically, the ratio of voltage to current is always changing depending on where you are on that curve. It's literally defined by this purple line, which is the slope of that curve at any given point. The rise over run, current over voltage, is 1 over R bulk. So when we need to use R bulk, we first need to know what our DC current and voltage is with respect to that interface. So we need to define what's known as an operating point. So we need to know how much current and voltage are flowing through the resistor, and then we'll use a little bit of math to define the slope, and then that slope will give us what's called dynamic resistance, which is really R bulk at that point. So you can see it changes because the slope changes as we go through the curve. So we'll practice doing that when we need to look at AC behavior across a PN junction, and we will use a very particular PN junction, which is the base emitter portion of a bipolar junction transistor, which is basically that end of the transistor is basically a little diode. So just keep that in the back of your head. R bulk the actual ohmic resistance for a diode changes depending on where you're operating the diode, how much voltage is across it and how much current's really actually flowing through it. Okay, now that we have a circuit model, and we're going to use model number 2 just as a hint, let's put it to use. Let's do a few examples here to put that model to use. So we're given example 2.1. I'm just going to talk you through the examples in Fiore's text, and you can work through them on your own, or at least I'll go through most of them. So we've got a real simple circuit. You'll probably build one of these in one of your labs. We have a DC voltage source rated at voltage equal to E. We have a diode D, and we have a resistor R. Somebody who's really smart, they put a current limiting resistor in their circuit so they wouldn't burn out their diode. So somebody wants to know, for this circuit, we assume the voltage is 12 volts and the resistor is 2 kilo ohms, and the diode is silicon, and it's got a bulk resistance of 10 ohms. So we got to use model number 3. So not model number 2. We do have to account for the bulk resistance in this circuit. And using the 3 diode approximations, compute the circulating current. So, okay, we're going to go through all 3. So what is wanted is how much current is going through the circuit. Well, we can start with the approximation number 1. If we didn't account for the forward bias voltage of the diode, basically it would act like a short, because it is going in the forward direction. We have positive current coming out of the battery, and you can tell by the direction of the arrow on the diode symbol that it's oriented forward with respect to the voltage source, so it'll act like a short. So the current's just going to be given by E over R, because the diode is not going to do anything other than act like a short. So that was pretty easy. If we include the forward bias voltage of the diode, the energy hill necessary to initiate conduction, or Vme, all means the same thing, then we got to know what that is. Well, we were told the diode is silicon, and we know that forward bias energy to jump the hill voltage for silicon PN junctions is about 0.7. So our knee voltage, where our current versus voltage curve for the diode really cants up, that's at about 0.7 volts. So basically we can look at that as a little voltage source put in opposing our source. So basically, if we were to look at apply Kirchhoff's voltage law, we could start at ground, maybe here on the negative terminal of the battery, and we're going to go up 12 volts as we go through the battery, and then we're going to step down 0.7 volts just to get over the hill of that PN junction. And after that, we just are going to drop the rest of the remaining portion of our 12 volts over the resistor. So we can write that. We can express that Kirchhoff's voltage law in this little equation. Mr. Fiore has kind of rearranged terms, but basically the voltage that we have left to apply over the resistor is the source minus that forward bias to get over the hill in the diode. So we'll have a little bit less current available to flow because the diode has got that opposing voltage. And of course, if we want to add the series resistance of the diode, it can just be lumped in with the other resistor because they're both in series. But our total driving voltage of the circuit is still discounted by our voltage source, and that is using, go back up, that last one is using this model. Okay, with the switch closed. With the switch closed because the diode is oriented going forward. Okay, so not surprisingly, the next thing that we get in an example, somebody wants to know, well, what if we turn the diode backwards? Then how much current flows through? Oh, and they crank the power supply up to 20 volts, and we still have a silicon diode, and we have a 2 kilo ohm resistor. So this is almost a trick question because this is in reverse bias, so it'll act like an open switch. Doesn't matter what the forward bias voltage is, it doesn't matter what its bulk resistance is. Basically, we have something, I'm going to go right back to those 3 models. Effectively, all of these models include a switch that is open if the diode's in backwards. So if the switch is open, it doesn't matter what the other components of the model are. So that's really important to remember when you're looking at circuits. When you see one of these in backwards, it's an open, so no current flows. I don't care what else is in the rest of the circuit. Arguably, if this source were beyond breakdown voltage, you might conclude, oh, it's some current could flow, but it's not a good situation. In that case, you'd say the circuit failed. But if it's operating properly, no current would flow. The diode's doing exactly what it's supposed to do, which is blocking current flow in the wrong direction, or in the reverse bias direction. Okay, what if we doubled up on our diodes? What if we did a twofer? We can actually use Kirchhoff's voltage law to kind of walk our way through this. So let's see which diode model we need to use. So we're told somebody wants to know the circulating current, or the circuit current, and everything's in series, so everything's getting the same current. So we only need to find one current. And somebody wants to know the diode and resistor voltages. Okay, good enough. Assume the power supply is 9 volts, so E equals 9. The diodes are silicon. Okay, that was really easy. That just told me one thing. I know the diode voltages now. These are oriented in forward bias with respect to the direction of current flow. I got my source oriented, so conventional current's going to flow clockwise. The diodes are inserted forward. I know they're silicon, so I know they're each going to have a voltage drop equal to that forward bias voltage, the hill voltage within the diode, so that's 0.7. So the drop over each diode is 0.7. The resistor voltages, or the voltage drop over the resistors, is of course going to depend on the current flowing through them. The same current is flowing through both, so I can do a little mental Kirchhoff's voltage law. I'm going to put a ground here at the negative terminal of the battery and say that's 0 volts. I'm going to go up 9 volts. I'm going to drop whatever the current is, times R1 to get to this point up here kind of at 12 o'clock. I'm going to drop 0.7 to get over to my upper right hand corner. I'm going to drop another I times R2 to get to my lower right hand corner, and I'm going to drop 0.7 to come back to my starting point. So there's my KVL loop around that circuit. And this is just a shorthand way of writing that KVL loop. So I know what the resistors are, I know what the V knees are, they're both 0.7, and so I can solve for the current. Pretty easy. Parallel configuration. So we can put diodes in anywhere. So now we have a parallel circuit. So not surprisingly, I'm sure somebody wants to know the current flowing out of the battery, and the voltage drops over the resistors, which if we know the current flowing out of the battery, we'll know the voltage drop over R1, V equals IR. But to get the voltage drop over R2, we kind of have to apply some parallel thinking, and that's good. We know how to handle parallel circuits. So we have our diode D and our R2 in parallel. What's the definition of parallel? What makes something be in parallel? Same voltage drop, right? Okay, what's the voltage drop over a diode? Well, it's equal to, and all things considered, it's equal to the forward bias voltage of the diode. So what kind of diode is it? It's silicon. So that means it's going to have a forward bias voltage drop of 0.7. Oops. Let's make sure it's oriented in forward bias. So here's the positive terminal of my battery. Current's going to flow out of that. It's going to flow clockwise. Yep, diode's in forward bias. Otherwise it'd act like an open. This would be real simple. But it's in forward bias, so I know from this node up at the top back to ground, that's a delta V of 0.7. That means there's got to be a delta V over R2 of 0.7. So I can apply Ohm's law to R2 knowing already what its voltage drop is, which is the same as this, and get the current through R2. So that's pretty easy. And so having the current through R2, then I have to go back and I can combine that and get a total circuit current. So Mr. Fiore walks us through that, but that's kind of the crux of it, is the current through R2. So how do I get the full current? I can go through my node voltages. I can apply KVL, and I'm using this parallel branch as a combo. I start at ground. I go up through the source, which is 10 volts. So my upper left-hand corner is at plus 10 versus ground. I drop I times R1 to get to this node, and then as I go from this upper node back to ground, I drop 0.7. Whether I go through the diode or through the resistor doesn't matter, I drop 0.7. So if E was 10, I drop 0.7 over this portion of the circuit, I know I got to drop 10 minus 0.7 over R1. So that's 9.3. I divide 9.3 by R1 and I get the current flowing through R1, which is also the current coming out of the source. Right back to basic definitions of series and parallel and Kirchhoff's voltage law. You're going to see Kirchhoff's voltage law again and again and again in semiconductor circuits, because it's a fabulous way of accounting for these fixed voltages that we get at every PN junction and throughout all of these semiconductor devices. So this is a great review of the basics that you learned in DC. Okay, there's a computer simulation you can run of that. I would definitely recommend you simulate all of these in TINA. In your simulation software. It's a great way to reinforce what you're doing, but also do some hand calcs. Okay, a little bit more complicated circuit, but not too bad. So now we've got diodes arranged in two different orientations. D1 is arranged in forward bias with respect to the source, and D2 is reverse. Okay, so all of our diode models say, regardless of whether you're using the simple one or the more complicated one with an R bulk, all of them say if they're reverse biased, they're open circuit. They're an open. So it might as well just go away. So we know right away, given the orientation of our DC source, no current flows through D2. We don't know what the voltage drop over it is. We haven't really defined it because it's basically not there. So we don't have an automatic measure of the voltage drop over this resistor the way we would have had this been forward. So we just take it out, kind of the way we took voltage sources out when we were doing superposition, because it's an open. So our circuit just becomes 20 volts, a 1 ohm resistor, D1, and a 2 kilo ohm resistor. So we could KVL this and say we go from a 0 volt a reference point, we go up 20 volts, we drop whatever our total circuit current is times 1K. We drop 0.7 over D1 in the forward bias. No current flows through D2. The same current that flowed through the 1K flows through the 2K, and that brings us back to ground. So we could say 20 volts is equal to 1K times I total minus 0.7 volts minus 2K times I total, and solve for I, which is exactly what Mr. Fiore has us doing here. So key points, who's in forwards and who's in backwards, and then you can redraw the circuit and KVL it. Okay, that is the end of our diode spec and diode models. And as a note, please apologize. I am personally in the habit of turning Kirchhoff's voltage law into a verb. I will very often refer to KVLing something. That is probably not strictly appropriate use of Kirchhoff's voltage law, but it is so powerful in circuit analysis with semiconducting components. I'll often use it as a verb just to reinforce how important it is to do. It isn't just a principle, it's an action plan. So please excuse my use of Kirchhoff's voltage law as a verb, and you can KVL your circuit, but maybe don't use that terminology as such in the workplace, unless your boss does the same thing. So, but you've now seen the power of Kirchhoff's voltage law using a diode model as just an opposite oriented voltage source primarily. You will use that again and again in very complicated circuits that become simple, because you can do that. So our next lecture is going to pick up here in our textbook section 2.5. We're going to look at specialty types of diodes that do amazing things in circuits, including this one here with a funny kind of kinked line in the symbol. That is the only diode where we deliberately can put something in reverse bias and operate it continuously. So that'll be our next lecture, so stay tuned.